Hello, everyone. I'm Thomas Cilloni from the University of Mississippi, and I'm here to present Ulixes, a facial recognition privacy system that uses adversarial machine learning. This is a collaborative project with Professors Wang from Xi'an Jiaotong-Liverpool University and Professors Charles Fleming and Charles Walter from the University of Mississippi. Let me dive straight into it. State-of-the-art facial recognition systems have become exceptionally accurate nowadays. You can think FaceNet achieves 99+% accuracy in facial verification tasks, and so do many other models. However, current legislation is falling behind, mainly because it needs to be interpreted on a case-by-case basis, and this does not offer strong privacy guarantees. Also, data can be moved to different jurisdictions, making it easy to avoid the law. Cameras, if you think about this together with the fact that cameras and video surveillance systems are nowadays everywhere, this is a strong privacy threat. One solution that researchers have found is to use adversarial machine learning, which is a set of techniques to reduce the accuracy of machine learning models. Now, if the accuracy of a facial recognition model is reduced, then privacy is promoted. Some examples of these recent solutions include Fox, presented in Usenix 2020, which is based on dataset poisoning, and Foggysight, also based on dataset poisoning, and FaceOff, which were both presented in PETS last year. Now, while these are great systems, recent research has shown that data poisoning often gives us misleading privacy measures, and we should therefore look elsewhere for stronger privacy measures. What we propose with Ulixes is a gradient-based adversarial algorithm to limit privacy threats in the context of pre-trained recognition systems, facial recognition systems. Its main advantage over literature work is that it does not require any data poisoning. It works against models that are not tampered with, basically. It's also fast on relatively mobile hardware like my business laptop's CPU, and provides empirically significant privacy improvements. Not all this shines as good, though. In fact, the privacy gains are dependent on the transferability of the adversarial perturbations in black box settings. Sometimes we find strong transferability, other times not. This said, however, we can use model ensembling to significantly improve the transferability of these attacks. Let me give you a background on facial recognition and adversarial ML. Facial recognition studies techniques to extract information from face images. Now, in practice, this means that we're working with mainly two tasks. Verification, which is a binary task given two images, tell whether they belong to the same person or not. And identification, which uses reference data set with many images of many people, and given a query image, tries to determine which identity it belongs to. Speaking of the adversarial machine learning, adversarial machine learning is the task of trying to reduce model utility by carefully crafting data points. This image, taken from Goodfellow's famous paper in 2014, shows you an example of this. A model is fooled into thinking that a panda is instead a monkey by applying an almost imperceptible noise mask that from this video stream you probably cannot even recognize. Let's now talk about the methodology and the algorithm of Ulixes. The threat model that we use is a game between an attacker and a defender. The attacker wants to correctly identify the defender among a small group of reference labeled images, while the defender is the end user, or unfortunately product, of a facial recognition service, and wants to cloak, to perturb their own images, to make them unrecognizable by the attacker. The algorithm is a gradient-based one, is a gradient-based optimization problem, where we look at the triplet loss, which tells us how more similar reference sample A is to a positive example with the same identity as A than it is to a negative example with a different identity from A. And we use a slightly varied version of this triplet loss to define the cost function of our optimization problem. So the target of our optimization is to find a perturbation that, when applied on our reference image A, makes it more similar to the negative example than it is to the positive example, and therefore it can be misidentified. A question now is, how do we select the positive and negative examples to use? For simplicity, we're going to use the positive sample. We're going to set the positive sample to be the same as the query image that we use, as after all, they belong to the same person. As for the negative example, we look at 5 different ways to choose this. We look at the feature space, the embedding space of the images, and we pick either the farthest example from the query image, or an example at random, or a combination of the two to mitigate the chances that randomly picking an example may not produce a good result. For the sake of completeness, we pick the closest sample in the feature space. And finally, we do not pick a negative example. We instead use the positive example with a slightly perturbation applied on it. Now, as for the results, first of all, here are the visuals of it. On the first row, on the top, you can see some sample images, original, uncloaked. And in the rows below, you see how they're cloaked by different algorithms, Ulixes being on the second row. From the video stream, you probably cannot tell the difference between the original images, Ulixes, and Fox, whereas face-off clearly shows significant perturbation. Now, as for the effect of how we pick the negative examples, let's look at this scatter plots. On the top left corner, you see the original uncloaked images, and you can see that they form many clusters with different colors. Now, this means that an attacker is able to correctly identify all these people, all these images of these people. And in the other scatter plots, instead, you see different ways to pick the negative examples, with no target and random, the two in the middle, being the most effective in scattering around the images in the feature space, introducing chaos in the feature map. With the no target approach, so using the as negative example, the positive example with a slight perturbation applied on it, being the most effective. And this is an effect of the reference data set depth and breadth on the identification accuracy of an attacker. The more identities an attacker has to choose from, the lower is the accuracy. And that's what you see on the Ashesa. Whereas the 3 rows tell us how many samples per each person the attacker has available. And you can tell that the more samples are available, the more powerful, the more accurate an attacker is in identifying users. However, when we go from left to right, so we applied our cloaks, you can see that the accuracy of the attacker is consistently reduced, as long as the problem is not trivial. You can tell that with 10 people in the reference data set, the attacker's accuracy is always below 50%. Now for the applicability or the transferability of these attacks. On the top row, you see the models that we use to generate the cloaks. And on the leftmost column, you see the models that we attack, that we try to defend from. Generally, as has been shown in literature, similar architectures transfer adversarial attacks very well, but they do not transfer well across architectures. So we use ensembling on the leftmost 3 columns to mitigate these negative effects and craft examples that transfer acceptably well across different architectures. Let me conclude with a couple of remarks. We've seen that Ulixes is an optimization-based adversarial ML algorithm that uses an evasion attack to increase the privacy against invasive facial recognition systems. And while fast and effective in controlled experiments, its applicability depends on the transferability of adversarial examples across models. And adversarial machine learning is a fast evolving research area. And until we can find mathematical guarantees, such as differential privacy in the context of tabular data to ensure privacy in computer vision, this remains one of the most promising research fields to promote privacy-preserving machine learning applications. This is the end of the presentation. Thank you for staying with me.